Hello everyone, my name is Timothée Hoffreumon, and today I will present you an article that I've co-authored with Ognyan and Oreshkov called the multi-round process matrix. So we'll follow the structure of our paper. That is, first I will introduce the multi-round process matrix based on the process matrix, and I'll introduce a few reminders of the process matrix formalism itself. Then I will move on to the two aspects of our result. That is a full characterization of the set of valid multi-round process matrix, or MPM, and then the extension of the notion of causal correlation and causal separability to the framework of multi-round process matrix. So a few reminders in order first. There exist quantum processes that do not rely on the assumption of fixed causal ordering. Such an example is the quantum switch, in which you have, in a sense, two parties, Alice and Bob, that are in a superposition of Alice being before Bob and Alice being after Bob. And so to represent this kind of processes, we can use the process matrix formalism. And this is not only an interesting theoretical aspect, but it also have practical advantages in tasks like communication or computation. It was proven that indefinite causal order can provide an advantage. But there is an issue with process matrix to represent such communication tasks. It's that it assumes that the parties only have one round of communication, that is, the party only receive and send one message during the process. But this is a bit complicated to represent real-life protocol, in which you typically expect the parties to have several rounds of message exchange with each other. So this is where we define the multi-round process matrix as a generalization of process matrix in which you allow the parties to have several rounds of communication. Let's take a few step backs and define the basics of process formalism and process matrix, so you can see how it relates to multi-round process matrix definition. So the premise is that you have parties, here Alice, that receive quantum system, act on it following the usual rules of quantum mechanics, and then send it away. So to represent that, we use the formalism of quantum instrument, that is, we associate with the operation of Alice a collection of CP map, each map being associated with an outcome that Alice observes. And these maps are from an input space of operator to an output space of operator. And if you sum up on all the outcome, you get a deterministic map that is represented by a completely positive and trace preserving map that is a quantum channel. So we work in the matrix representation of these maps. So we use Choi-Jamelkowski isomorphism to represent the map by operator on the tensor product Hilbert space. That is, it will be matrices. And so the complete positivity in matrices is translated by the fact that matrices are positive semi-definite, whereas the trace preserving characteristic is translated into the trace of the matrix being equal to the dimension of its input. So with this premise, the process matrix framework consists of taking several parties, here Alice, Bob, and Charlie, for example, that communicate with each other using sending and receiving quantum systems. So we represent everything that is outside of the control of the parties by a big overall functional that do not assume causal order. That is, the functional do not assume, for example, that Alice is before Bob. But and this functional takes the choice of quantum instruments and associate with each element of quantum instrument a probability of observing outcome. So when we go to the Choi-Jamelkowski picture and we represent the functional as a matrix, the matrix that you obtain is called the process matrix, or PM. And there is a notion of Born rule here. So that's the probability of observing certain outcome. Here I do my example with three parties. So the probability of observing these outcomes is given by some kind of a Born's rule, in which W can be interpreted as a generalization of the density operator, but also encodes the communication between the party and not only the state preparation, for example. And we say that W is normalized on quantum channel. That is, when the parties input quantum channel or deterministic operation, it should give you a probability of 1. Now, to extend this framework to multi-round process matrix, what we want is to have parties to be able to have several rounds. So here, for example, Alice have 2 rounds, and in between her 2 rounds, she can keep memory outside of the process. This memory can be classical or quantum, and otherwise it's the same. So you still have no notion of causal ordering between Alice and Bob, but here you have a restricted notion of causal ordering that is added, that is caused by the memory of Alice. So that there is a first operation of Alice, then a second, and if you were extending, there would be a third, fourth, etc. So to represent the fact that the party can have more than one operation, we use a generalization of quantum instrument that is called quantum combes. And in matrix representation, this is represented as such. So here's a diagrammatic representation of the previous situation in which Alice have what we call a 2 comb, that is 2 teeth representing 2 operations, and a handle of a comb representing her memory or side channel in between her operation. Whereas Bob had only 1 operation, so it's still a usual quantum instrument. And now if the process is normalized on deterministic quantum comb, we say that this process is a multi-round process matrix instead. This operator is a multi-round process matrix instead of a process matrix. Remark here that if there was only 1 party in the experiment, so if Alice was alone, then W had to be quantum comb itself, so deterministic quantum comb itself, because it's what is normalized on single quantum comb, it's quantum comb. Whereas if the party were limited to having only 1 round of communication, then we are back to the situation of regular process matrix. So following the same argument as in the original process matrix paper, we can prove that an operator W is a valid multi-round process matrix if and only if it respects the following 2 conditions. So the first condition states that the functional should be completely positive, because you want to be able to extend your party's operation with ancillary, and this ancillary can, the functional on this ancillary have to be completely positive, otherwise you can mess the probability and have negative probability. And the second condition is the normalization of probability, so that W should be normalized on quantum combs. But this last condition is a bit uneasy to handle, because you have to consider any choice of any deterministic quantum comb that the parties can make. So this is not very easy to see the structure of W from this. So this brings us to the first aspect of our result, that is an easier way of characterizing W from this condition. What we do actually is to extend the technique that was developed in a previous paper to characterize the process matrix. And what they've found is that in the bound rule, the operator you plug into it are defined on subspace of operator. And you can characterize this operator actually simply by finding the projector onto this subspace. So our method will follow the method, but here we use it for multi-round process matrix and general things. So it consists of first finding the projective characterization of the object you want to plug into your multi-round process matrix. And when you have this characterization, you can deduce a projective characterization of your multi-round process matrix from it. So to do so, we first need to find the characterization of deterministic quantum comb, a single deterministic quantum comb. This is the following condition that we prove in our paper, in which P is a projector that is, of course, depending on the number of teeth that your party have. The first 2 conditions, you can notice that it actually states that a deterministic quantum comb should be quantum channel, and then you restrict the space of quantum channel, because the set of quantum channels, sorry, because you don't want all the quantum channel to be deterministic quantum comb, because you have this notion of the first is being before the second is and before the third is, etc. So you have to restrict the channel to only the channel that respects this kind of condition. So with this characterization of one quantum comb, we can find the characterization of the quantum comb of several parties. So we use tensor composition. And we have that the condition follow directly, because tensor composition of positive semi-definite matrices is still a positive semi-definite matrices. The trace of a tensor product is the product of traces. And the overall projector is obtained simply as taking the tensor product in the superoperator space. But M here, defined as such, is not exactly the set of deterministic quantum comb taken into tensor product with each other. No, it's a bit more than that. Actually, it's the span of this set and restricted to affine combination, so that M, as defined with this condition, is the set of affine sums of tensor product of deterministic quantum comb, but it do not cause a problem for characterization for what we want to do, because the trace is a linear mapping, and in a linear mapping, if W is normalized on tensor product of deterministic quantum comb, it will be normalized on affine sum of deterministic quantum comb, so that we can carry on with this slight remark. So now that we have the projective characterization of the object we want to plug into our process matrix, we arrive at our first theorem that links this set of conditions to the condition that we want to impose on our operator W in order to be a valid multi-round process matrix. Again, remark that the two first conditions are hinting that this is a quantum channel, but you can see here it's the output that you get for the trace condition. It's as if the multi-round process matrix was a channel in the opposite direction as the deterministic quantum comb you want to plug into it, and thus overall, when they are composed together, they form some kind of a loop. And then for the projective the projector characterizing the space of valid multi-round process matrix, you see that it's the quasi-orthogonal orthogonal complement, sorry, of the original projector plus the span of the unit matrix. You have to add the span of unit matrix, otherwise W would be traceless. And of course, if it was traceless, it couldn't be trace preserving, and you would mess your normalization of probability. I'm now doing a quick mathematical parenthesis here, because you can see that M actually forms a subalgebra of a matrix algebra that is characterized by this projector. And actually, W is what we call the quasi-orthogonal to this algebra when it has this formula. Anyway, this is a parenthesis. Now we can carry on with our characterization and ask the following question: what is actually the subspace that is defined by this projector? And this brings us to our second theorem, that is the fact that multi-round process matrix and process matrix by extension are nothing but affine sums of deterministic quantum comb that are normalized on the comb or the channel you want to plug into your process or multi-round process matrix. So as an example here, you have multi-round process matrix in which Alice has 2 operations and Bob has 1 operation. And what the theorem tells you is that this can always be decomposed as 3 deterministic quantum comb that respects the local causal order of the different party. That is, the second operation of Alice can never be before a first operation, but otherwise between Alice and Bob, they can be anywhere they want in the causal ordering relative to each other. So this concludes the characterization of the set of valid multi-round process matrix. And now that we know what is our object, we want to know what is the process that our object is representing. So a question that interests us is to tell when a given multi-run process matrix is representing a process that have a fixed causal order or causal correlation. To do so, we expand two notions from the original process matrix framework. The first notion is causal correlation. That is a theory-independent constraint you impose on the correlation the parties observe to say if the process is causal or not. And to extend it to multi-round process matrix formalism, what we have to do is to add as extra constraint the requirements that the local causal order in between the successive operation for a single party is respected. And then the second notion that we want to extend to multi-round process matrix is causal separability. So now it's a more theory-dependent notion, and it depends on the structure of your operator W. And if W can be decomposed or unraveled as a sequence of operation when you can say which party is first, which party is second, etc., then you say it's causally separable. Of course, this decomposition should be valid for any choice of operation by any party and any extension by any ancillary in between the parties. And what we found is this notion is also valid for multi-round process matrix if you also consider side channel in between the operation of the same party. So here are a few other sources about these two notions. And now let's focus on the definition of causal separability. So the definition of causal non-separability for multi-round process matrix actually tells you the following. If you have an operator W that is causally separable in the sense of multi-round process matrix, it means that if you take this operator as being a process matrix and you extend its size by side channel between the successive operation of a party. So here, for example, Alice has two operations, so she can expand her side by a side channel in between a first and second operation. But Bob here has only one operation, so he cannot extend his side. If Bob had three operations, he could extend his side by two side channels, for example. And then when you have done this extension, you have an overall process matrix that is obtained by composing the side channel with the operator W. And if this overall process matrix is causally separable in the sense of process matrix, then it will be causally separable in the W will be causally separable in the sense of multi-round process matrix. So now you can think that if you have process W, matrix W that is causally separable in the sense of process matrix, well, since you only extend it by a side channel, you can think that causally separable in the sense of process matrix is sufficient to ensure causal separability in the sense of multi-round process matrix. But actually, we show by an example that is not true at all. What we show is an activation. So given an operator W that is both a valid process matrix and multi-round process matrix, we show that in the first case, it will be causally separable process matrix, whereas in the second case, because you can extend it by a side channel, it will be causally non-separable, and it will lead even to non-causal correlation. So to prove it, we provide the following example. So we have an operator W that is shared between Alice having two operations and Bob having one operation. We put all the dimension of all the quantum system to be 2 so that we can work in the Pauli basis. So the operator have this formula in which we have used a shortened notation like that, in which we imply the tensor product and the identity so that we lessen clutter. And this operator W can be proven to be a valid deterministic quantum combe when you take this causal ordering between the operations. If it's a valid deterministic quantum combe, this means that there exists a physical realization of your process, and also that the correlation you will have always will be causal. And as it's a valid deterministic quantum combe, it's especially a special case of causally separable process matrix. But also, if you do not assume a node ordering like that, but instead you assume that the first node of Alice is before a second node, then it's still a valid causally separable process matrix, but it's now also a valid multi-round process matrix with this ordering. And this valid multi-round process matrix, however, is causally non-separable. We will now prove the causal non-separability by the following protocol. So if Alice chooses to extend her side by an identity channel, which she can always do, and then forward the first input toward a second operation using this side channel, and finally she measures in the X basis her second operation, then you will have a restricted process matrix between the remaining open wires of Alice and Bob. And this restricted process matrix have this formula in which you have a plus or minus sign that depends on the measurement outcome of Alice, so that Alice can simply change her basis in order for this sign to always be a plus sign. And when you have this formula, we can remark that this is actually the process matrix that Oreshkov, Costa, and Bruckner proposed in their first paper introducing the process matrix as an example of a causally non-separable process matrix, which moreover can be used to achieve non-causal correlation, because it beats a causal inequality, which is a way of certifying that you have a causal or not correlation. Therefore, we have seen that allowing this side channel makes the process matrix W that was causally separable a multi-round process matrix W that is causally non-separable. So to conclude, our idea was to introduce the multi-round process matrix, which is a generalization of the process matrix in which you allow the parties to have more than one operation, because we were motivated by the fact that in real-life communication protocol, parties can have multiple rounds of communication and keep a memory of the previous operation on outside of the process. So our results were the following. We first fully characterized the set of the validity condition of multi-round process matrix. We linked it to the set of valid deterministic combe. Then we have extended the notion of causal correlation and causal separability to the case of multi-round process matrix. And by an example, we have found that these notions are different than the notion defined in the process matrix formalism. So now what we can do next will be to, of course, use the tool that we just defined to find new protocol that gain an advantage of using indefinite causal structure, so that it's better at doing certain tasks in communication, computation, etc. But also we can use the technique that we developed in our paper to look for even higher order generalization of process matrix and order generalization of quantum theory to see, for example, if there is an equivalent notion of causal correlation for the higher order. So this higher order that I'm talking about were defined in a previous paper. And if you want a taste of how to quickly define a higher order generalization, you can take an operator and normalize it on, for example, the tensor product of process matrix, and this will be some kind of a higher order quantum process matrix. So thank you all for your attention. I'm conscious that this was a very technical result, so I can only invite you to read the paper if you want to have more details. I would like to thank the QPL organizer for having me to this conference, and I bid you a good day and see you. Goodbye.